So good evening to all. So in the today's session, we're going to see the multiphase flows. First, we're going to see what exactly are the multiphase flows and how we're going to model it using OpenFOAM. So what exactly is the multiphase flow? So whenever there is an interaction of more than two phases of fluid, more than two phases of fluid, we can call it as a multiphase flows. So it can be like interaction of air with water, or some oil or some viscous fluid with water or with air. It can be considered as multiphase flows. So in the today's session, we're going to see these two benchmark problems, which is bubble rising using Weir's model and fluidized bed using mixture model. And both these problem is modeled with two different approaches in OpenFOAM. One is volume of fluid approach and one is Eulerian multiphase flow model. So coming to the first problem, which is the air is entrapped inside the continuous fluid, or let's say the blue zone is air and the red zone is water, and how the bubble will going to rise inside this continuous phase, we're going to see. So this is the basic geometry details of this geometry. So in VF model, that is volume of fluid model, we're going to numerically track the interface of the bubble. As you can see, the interface of the bubble is traced. So in the subsequent slides, we're going to see how the surface or the interface of the bubble is being traced. So for which some governing equation we're going to solve, starting with continuity equation and Navier-Stokes equation. So this is the most common equation which we're going to use for any fluid flow simulation. Apart from this, as we are seeing the interaction of two different phases, so surface tension will come into effect. So this is the source term which will which is act as a source term in the governing equation for the surface tension effect. Now, further going forward, how we're going to resolve the interface of the phase. So for which this alpha denotes the phase, and it will also vary from 0 to 1. So 0 denotes the air phase or lighter phase, or 1 denotes the heavier phase or the water phase for this kind of application. So alpha denotes the phase of the fluid. So using this equation, we're going to trace the interface of the bubble. So there are various methods dealing with how we're going to trace the interface. That I'm not going to detail. Just the basic idea is this additional equation will going to decide how the interface is being traced. So as I've shown, this is the boundary or the geometry details with boundary condition. So these two are the no slip boundary are the wall with no slip boundary condition, and this is the pressure outlet. So that means the bubble will going to escape from this computational domain. Sorry. So let's go to the test case. So this test case later on I will going to share it with you all. So this is the common setup of the OpenFOAM, consists of 0, constant, and system folder. So for a single phase flow, let me delete this. So for a single phase flow, only U and P file usually used to be there. So U is the velocity of the flow field and P is the pressure of the flow field. Now here we are seeing the interaction of the two different phases. So one additional file will going to appear, which is alpha phase. So as I've said, alpha is the phase of the fluid, which are going to distinguish or are going to resolve the interface. Now, apart from this, if you'll see the constant folder, so here the turbulence property, going to see. So turbulence property. So for this simulation, we're going to consider it as a laminar flow. In the transport property, we're going to specify the properties of the two phases, whether it's a Newtonian fluid or non-Newtonian fluid, what is the kinematic viscosity of both the fluids, and density. And apart from this, as I've shown in the governing equation, the surface tension will come into effect. So here we're going to specify the surface tension. So for now, we are simply taking some random values. So this is so phase one is the heavier or continuous fluid, and phase two is the entrapped fluid. And this is the file which will include the gravitational force. Further, in the system folder, FE scheme and FE solution will going to tell us what discretization scheme we're going to use and what metric solver we are using to solve this pressure, velocity, and alpha phases. So apart from P and U, so as you can see, so pressure and velocity is solved using the standard Gauss-Seidel metric solver. And similar to this, we're going to solve alpha phase. So here we have specified the alpha phase. Now, we'll go directly to the our OpenFOAM interface or Ubuntu interface. So for solving this problem, I'm using OpenFOAM 2412. So I'm initializing it using OpenFOAM 2412. So after being initialized, so how we're going to tell these files that where my bubble will going to lie. So as I've showed here in the geometry details, that from the walls, the center of this bubble is 0.5 meter away. So that we have to specify in the set field file. So here we have to specify the phase and at what distance it will be from the wall. So as I've said, the continuous phase is water or phase one. So default value for the phase is 1. And now we have to specify the second phase. So how we're going to specify? So we are simply solving a 2D computational domain. So for which I'm considering it as a cylindrical to the cell. We're going to define two points that I'm going to show and the radius. So using these 2 points and radius, it will going to draw a circle in the computational domain with the phase of 0 or phase value of 0. So this is the 0 folder where we're going to define the boundary condition. So as you can see, at all the boundaries, I have defined a zero gradient boundary condition, and front and back is empty because it's a 2D case. And using set field, so currently there are no values defined inside this file, and internal field is defined as 0. So using set field boundary condition, once I will initialize this field, we'll able to see the two phases in the computational domain. So for which I will use this set field. So set field option is mostly used for initializing the flow field. And here also we are initializing it for defining two different phases. So once I will initialize it, you can see it has defined, or it is setting up the volume for two different phases. So the default phase is the alpha with alpha value of 1, that is a continuous phase. And here using these 2 points and radius, it will going to define the circle or the second phase. So that we're going to see how it is defined. And before that, we can see that in the alpha file, now it has initialized this file with the internal field of some values of 0 and 1. So if I'll open the parameter to visualize it, we'll able to see two different phases. So here you can see that we have successfully initialized the two phases, and here is our circle or a bubble entrapped inside the continuous phase, which is 0.5 meter apart from these two walls. So to solve the interaction of these two phases, we're going to use interform as a solver. So as this is a very coarse mesh, let me show you the mesh also. I've not gone into the details of block mesh because that is already been covered. So it will not take much time, and it's a 2D case, so it will not take much time to solve this kind of simulation. Stop it. And now if I'll visualize it, you can see how these two phases are interacting, and the continuous phase is disrupting the second phase, and how the bubble is rising inside the continuous phase. Now, similar to this, here we have only seen how to initialize the single bubble. Now, similar to this, if I want to simulate the interaction of two different bubbles in the continuous phase, so what I have to do, I have to define the same, or I have to redefine the second bubble by changing this point. And we can change the radius also, or if we want to see the interaction of the same size bubbles, that is also fine. So I will do one thing. I will simply change the height of the bubble or the location of the bubble in this y direction, and I will change this also. So now the first bubble will be of radius 0.25 and the second bubble will be of radius 0.15. So using this set field, we can define as many as bubbles, and we can study the interaction of them. Delete these files. Now again, I will run the set field command, and you can see uh, this is the first bubble and this is the second bubble, and both are initialized in the computation domain. Uh, we should visualize it also, because randomly we are giving the points for the initialization. So we have simply defined, and both the bubbles are overlapping. So it will be better if I increase the height so that it should not interact before. So okay, now we run set field. So as you can see, we have initialized these two bubbles. And again, by running the interform, we will able to see the interaction of these two bubbles with each other in the continuous phase. So in this case, you can see how these two bubbles are rising inside the continuous domain. And by changing the height, because this is simply a random case, we'll able to study the interaction of these two bubbles with each other. So this was all about the VF model, that is volume of fluid model, where we can easily trace the interface of any phase. Uh, so this we are using this volume of fluid method we are using, where we can easily trace the interface of any phase. However, in some of the application, it will be very difficult or it will be computationally very expensive to trace the interface of any phase. So for such kind of problems, instead of tracing the interface, we'll simply uh, see the overall effect where the phase is changing or where the two phases are interacting with each other without resolving their interface. So such methods are called as Allen uh, multiphase flow model. So moving forward with that, so this is a classic example of Allen multiphase flow model. So this is a fluidized bed. So fluidized bed is a bed of, for example, sand. From the from below some, we are injecting the high pressure fluid or air, and because of the interaction between the high pressure of air and the sand will start to behave like a fluid. So instead of resolving the each and every particle of the sand, we'll treat it as a continuous phase, and we're going to model the interaction between this sand particle with each other. So, so that's what I was saying. So instead of resolving the interface of some phases, we're going to model it, and we're going to see the overall effect uh, in the simulation. So instead of resolving these bubbles or particles or phases, we're going to average the phases or uh, average the weightage of these phases in terms of void fraction. So so that we're going to see the overall effect of each phase. So same equation we're going to solve for this kind of application. So in VF approach, we were separately solving continuity equation, momentum equation, and phase equation to resolve the phase of each, or to resolve the interface of each phase. However, in this, we're not going to resolve the phases or the interface of the phases. So for that, we're going to solve the governing equation for each phase. So suppose there are two phases, but instead of resolving the interface, we're simply going to model it. So suppose air and water is being interacted. So total four equations we're going to solve. So two continuity and two momentum. So one each for air and water. So similarly, in case of this fluidized bed, so it's a sand bed which is interacting with the air. So this is the alpha S. So S, we are denoting the sand bed as solid bed, and air is impinging or air is ejecting from the bottom of this bed. So it is we are treating it as a gaseous phase. So continuity equation for these two phases, and again the momentum equation for these two phases. So if we're going to resolve the interface, or like in the volume of fluid method, if you want to resolve the interface of any phase, uh, directly we can calculate the forces impacting or changing the shape of the phase. For example, drag coefficient or drag force we can easily calculate by seeing the shape of the phase. However, in this method, we are not resolving any interface. So additionally, we have to include some of the forces to model the or to take the effect of those forces. So the drag force will additionally add in this momentum equation. And there are various drag models which are available in the literature. So one of the drag model which I'm showing it here. So coming to this fluidized bed problem. So this is a continuous. So this blue one is the air phase or gaseous phase, and this red zone is showing the sand bed. So here also we are going to initialize uh, which I've showed it here using set field dict file, and air will going to so it this bottom wall is the air inlet from where we're going to inject the high pressure air, and how the sand bed or any particle bed will going to interact with this high pressure fluid. So that we're going to see. So let me show you this also, that this case is available in the open form case files. So let me show you as I'm using openform 2412. So where it will be. So inside this tutorial, if you go to multiphase, so there are numbers of various tutorials are given based on the uh, what kind of solver or what kind of application you want to see or you want to study. So we are simply seeing the interaction of two different phases using Allen approach. So and it is not reacting, that these two phases will not going to react with each other. So we'll going to see this two phase Euler form, and inside this also three sub folders are there: laminar, LES, and RAS, that is RANS. So if I will simply open this laminar, so you can see this fluidized bed problem is there. So I am going to demonstrate this fluidized bed problem only, and later on for a practice you can modify this problem. So you can see that now in the zero folder, that is the boundary condition file, many files are being appearing. So what are these? So for whenever we are solving a single phase problem, only pressure and velocity file should be there. Now, when I was demonstrating the first case, that is bubble rising case, one more file was there. That is the alpha phase. Because there only single equations we are solving for resolving the interface. But in this case, uh, each phase will going to model, or each phase will going to solve using different equations. So suppose air, we'll take it, for example, air. So for air, we're going to solve momentum equation and continuity equation separately. And for the solid phase, that is the particle phase or sand phase, we're going to solve continuity and momentum equation separately. So that's why sorry, the alpha particle is there and alpha air is also there. Yeah, this one. And similar to this, the other files are also appearing. So U air, U particle. So we'll quickly go through these files. So this is U particle, that means the velocity of the particle. So as I've showed, or we can again see it, that it is a steady bed. Means it will, unless we are giving the air inlet, it will not going to move anyhow. So that's why the velocity everywhere is given 0. However, when we'll see the U air, so for which we have given the inlet velocity and outlet also, means pressure outlet. So which means that air will going to leave the computational domain, not the particle phase. Now moving forward, uh, there are some other files which are also appearing in the constant folder. So turbulence property, and again here, as we are solving different equation for different all the phases. So turbulence property for particle, that means solid phase, and for the air phase, we have to define separately. Also, the thermo physical property of all the phases we have to define separately. So I will going to show all these files. Yeah. So coming to the turbulence properties. So here we are modeling both the phases using RANS, that is Reynolds average neighbor strokes. And we are also modeling the interaction of, so as I've said, this is a send bed. So the interaction of each particle of the send, we have to model it using some equation. Or so this we are modeling using kinetic theory, and the drag or the interaction between the particles, uh, for which we are using this Jackson-Jackson model. So it is going to calculate the friction between the when the two particles are going to interact with each other. It is going to calculate the friction between this particle. Uh, Coming to the air, as it's a continuous phase, so only we have to define whether it's a laminar or turbulent. Now, in the thermophysical property of the particle, here we have to define the molecular weight. What is the density? Cp is the specific heat. And as this is a solid phase, so we don't have to define any viscosity for it. However, for air, we have to define the viscosity. Apart from this, as I've said, that some additional forces we have to model in this Eilerian framework. So for now, we can use lift force, drag force, and other forces like viscous dissipation force in the air. But for now, we are only restricting it to drag force. So drag force, here we have to specify whether it's a drag of which phase on coming from which phase to which phase. So here we are defining that particle in air. That means the drag force which is going to impact the particles because of air. So for which we are using this the default drag model which are already available in open form. And again, this is the gravitational file. Now coming to system folder. So this will be the same like control date FE scheme and FE solution. And even the set field will also be the same, where we have to define the phases. So as it's a box type computational domain, so earlier I've showed that we were initializing the bubble using the cylindrical to cell. Now here it's a 2D box type computational domain, so we have to define the box for defining the particle or the phase. So the default value we have given is 1, and here up to what height our send bed will be there. So that we are defining using this box to cell type initialization. So we'll go to that folder and we'll see how the interaction of solid bed with air. So again here we'll start with block mesh. So there are only three walls, inlet, outlet, and two side walls. And front and back we are keeping as empty. Now for initializing, we are again using the set field initialization. So we can visualize this is the alpha particle. So this red zone is the send bed, and this blue zone is the air phase or continuous phase. And from this bottom wall, this is the inlet. It's not a wall; it's a inlet patch from where the air will going to enter inside this bed. So for this, as I've shown, we're going to use two-phase Euler form as a solver. Okay. So for this, I've used reacting two-phase Euler form. So it's a this both the solver are almost same. Only changes it can also suppose two of the phases are showing some reaction. So that this solver will also facilitate with the reaction between two phases. Apart from that, both the solver are same. However, in our case, we are not showing any reaction, so it is not going to solve the reaction between the two phases. It's not reacting two-phase Euler form. However, it will take some time. You can see or check the simulation till 0.1 second and we'll stop it. So you can see because of the air pressure, it is displacing the whole bed. And as I have not saved much file, so we're not able to see the animation of it. For that, let me show you. how the bed will going to react when the pressurized air will enter from the bottom. So this fluidized bed technique is being used by many industry because under the influence of any fluid, the solid bed act as a continuous phase or fluid phase. So this is used in many chemical industry for proper mixing of the solid material without using any viscous fluid. I will stop this. So this was the overview of the multiphase flows, where I have shown two different approaches. One is volume of fluid approach, and the second is Eulerian multiphase flow approach. So, if you have any question,
I had a doubt, but it's not regarding this week's lecture. It was regarding last week's lecture.
okay,
Um, so the thing is like I have imported an STL file into my Paraview, and
okay,
I want to define various patches within the STL file. So like um, I want to like define. Actually, the STL file was it was made up of different STL files, and then I merged those STL files, and now I want to define various patches like inlet, outlet on the different surfaces of the STL file. So how can I do that? Because I tried searching for it a lot online, but I couldn't find any sources on it.
no, one thing you can do when you are importing all the parts and merging it into one. So before that itself, you have to give the name of all the patches. That can be one of the option. And second option, let me search.
But the thing is, in the SolidWorks, it is not possible to name all the surfaces like that.
No, no, it is possible in in SolidWorks. You are saying, okay. Ivan, do you have any idea about this? Or
So the thing is, when I tried searching for the topo set deck online, like how can I um, define various surfaces within my STL file? It mainly just gave me like solution for like box to cell or like cylinder to cell. There was no specific mention for like how can I define a specific STL file and like give it some properties like maybe I can call this surface metal and like the surface adjacent to it water or something like that. And yeah, and other than that, also like within the create patch deck also I tried searching for it, but there was no STL file. I couldn't find sources on STL file. So if you can show me how to define for that STL file, like just a demo, it would be really helpful.
Arnav, if you are comfortable, can you just tell ki what type of problem you are trying to simulate?
Actually, I was trying to simulate. Basically, it was a composite cylinder, and the heat would. There was a water heater at the center, and the heat would flow from its center to its outskirts.
Okay. Okay.
So mainly, I wanted to make an inlet at the center of the innermost cylinder, and that's how the heat would pass through its outskirts.
Okay.
And I had one more doubt. This was just a thing that I came across for block mesh for SnappyX mesh. If I have a very huge block and I have a geometry within that huge block, and I make another block near the geometry, and then I snap those two blocks on the geometry. So will it be like more? Will it try to give me more finer mesh, or like is it something like not possible within open form?
So you want to give the finer mesh at some particular region, right?
Yes. So like if I snap another block near the geometry rather than snapping the entire block mesh, that which is defined outside the domain. So will it like give me more finer mesh, or like is it not
No,
possible?
that in the snappyhex file itself, you have to define the region where you have to give the local refinement instead of going for other blocks.
Okay.
Or you
Because
can use a utility in Snap itself. It is called as box. So around your region, you can create a box refinement. So
okay.
to input minimum and maximum coordinates, and then around the domain of interest, a box will appear. So you can refine a particular region using that as well.
Okay. Thank you, sir.
Hello, Paris. I have shared that form with the students, so they will send that case study topics. So probably I'll be able to share with you in another couple of days' time.
Sure, sir.
Okay.
Sure. Yes.
So it should be different from that provided in the case study list, right?
Yes, sir. So, I mean, it might happen that some student might take a case study that we have already in our repository. So, to avoid the conflict, we are doing this.
Oh, okay.
Anything else, sir? Any doubt?
And since we have students from like first year to final years, like is it okay? Like first year and second year, they can maybe two of them can join together and work for the case study.
Yes.
Yeah.
Okay, then maybe we can.
Yes.
Call today's session.
Okay. Thank you.
Yes.
Thank you, Nikhil.
Thank you, Nikhil, sir. Thank you. Thank you, Ashish, sir.